Okay, so let's start today's class. Okay, now we are going to session 5.3, this square problem. And at the beginning, I would like to briefly review the beginning part of this session, because in the last week, we have already briefly introduced the beginning of this square problem. So let me very briefly review this part. So now, the most important problem we want to face is we would like to find a least square curve to fit a set of data points in the plane. So we usually, in the engineering problems, we will collect a set of data points, and we would like to find a curve that could most appropriately describe the thread of these data points. So in this case, we would like to find a good curve to describe the distribution or the thread of the data points. And what is the so-called the best curve? This curve would provide an optimal approximation. It is in the sense of the sum of square of errors. So the so-called best curve means the square arrow between the curve and the data points is minimized. Okay, so this is the so-called best curve. Okay, for example, we have the data points like this, and if we want to find a straight line to fit the thread of this data point, we may find this straight line. And based on this straight line, we can see there are some arrow here. This is arrow, this is arrow. And we can also find another straight line like this. And which one is better? The better one is the straight line that minimize the estimation error. So in this sense, in the linear algebra, we just need to find the so-called least square solution. So a least square solution to an overdetermined system means usually an overdetermined linear system means that we have more equation than unknowns. And as we said before, one equation means one constraint. So if you have many constraints and you have fewer unknowns, that means an overdetermined system is usually inconsistent. That means no solution, right? If you have too many constraints, you may not be easy to find a solution to satisfy this linear system, right? Okay, so now if we have a linear system AX equals to B, if the matrix A is an M by N matrix, where M is larger than N, that means we have M equation, N unknown, right? So this is an overdetermined system. So we cannot expect, in general, to find a vector in Rn such that Ax equals to B, because you request too many constraints. So usually this kinds of linear system has no solution. Okay, so in the case of no solution, the next target of solving this linear system would be we just look for a vector x in Rn for which Ax is closer to B rather than equal to B. Okay, and this kinds of vector x, the closest the vector x hat, so that the Ax hat close to B That is the so-called least square solution. So in an overdetermined system AS equals to B, we would like to find the least square solution. And the arrow between the original B and the least square solution AX is called the residual. Okay, and we want to make this residual as small as possible. So we want to minimize the residual. Okay, and in these kinds of optimization problem, minimizing the norm of the residual is equivalent to minimizing the square of the norm. Okay, the final result is the same. So we want to find a vector S hat that minimize the residual, the norm of the square of the norm of the residual. We call this kinds of vector S hat is a least square solution to this system, right? So if S hat is a least square solution to this linear system, and if let P equals to A times S hat, then P is a vector in the column space of A that is closest to B. So you still remember that if we multiply A with some vector X, the result of AX should be in the column space of A, right? You already know that. And of course, when we substitute S hat, we substitute X by X hat, and that P equals to AS hat, then P obviously it should be a vector in the column space of A. Okay? And that is closest to the vector B, because right now AX would not equal to B, would never be equal to B. So that there's no solution for this linear system. Okay? Such closed vector P not only exist but also unique. Okay? So here is an illustration. The subspace S it's a subspace of Rm, and actually this is the AX. Okay, it's the column space of matrix A. It's actually the column space of the matrix A. Okay, and now the vector B is not in the column space of S, so that there is no solution for this linear system, right? And now we want to find the vector P, which is on S and is closest to the vector B. For any other vector Y on the subspace S, the distance between Y and B and Y, that is this, would be larger than the distance between B and P. Okay? So for any other vector Y not equal to P, the norm of B minus Y is larger than the norm of B minus P. Okay? So we call P is the closest vector of S, in S. Okay? P in S, and it is closest to B. Okay? And the residual, or the arrow, is calculated by B minus P, which is actually in the orthogonal complement of the subspace S. So B minus P is in the orthogonal complement of S. So we can see here, actually P and B minus P would be orthogonal. will be orthogonal. Okay, so let's skip the proof. And if the vector b is in S, then obviously AS is equal to B. Then this linear system has solution. Okay, if B is in S, and in this case, we have B is equal to P minus Z, P plus Z, where P is in S, and Z is in S perp. However, because B is in S, so actually B is equal to B plus 0, where this P is equal to B, this Z is equal to 0. Okay, so in this case, that means this is S, and actually B is like this. In this case, B is equal to P, and there is no arrow Z. Okay, so a vector X hat will be a solution to this square problem if and only if P equals to AS hat is the vector in the column space of A that is closer to B. Okay, and we can also say the vector P is the projection of B onto the column space of A. That is this. The vector P is the vector B, the projection of the vector B onto S. Okay, so this is what we told you before. So here are two examples. If the column space of A is one-dimensional and vector B is here, then the projection of B onto R of A is this P, and this is the residual. And the residual is in the orthogonal complement of the column space of A. Here is another example. If the column space of A is a plane, and B is a vector in the three-dimensional space, then the vector P is the orthogonal projection, is the projection on R of A, and the residual is in the orthogonal complement of the column space of A. Right? So this is the early introduction of the so-called least square solution. Right? OK， 好，所以这个部分呢，其实讲了半天，就是在讲什么叫做最小平方解。最小平方解指的就是因为我现在要求 AS 等于 B 嘛，那今天你如果是一个 overdetermined 的 system， 你就找不到解啊，你很容易找不到解。你找不到解怎么办？你只好退而求其次，去找最小平方解。好，那找不到解，它在几何上的意义是什么呢？就如同是这个，我 A 的 column space 可能是这个平面，而 B 这个向量不在 A 的 column space 上面，所以你就找不到解嘛，对不对？我们之前讲过，我们这个线性系统要能够找到解，那就是你这个向量 B 要在 A 的 column space 里面嘛。好，那现在 B 就不在 A 的 column space 里面，所以找不到解，那只好退而求其次，去找最小平方解。我去找落在这个平面上与向量 B 最接近的那个向量，那就是这个向量 P。OK， 好，那这个向量 P 等于谁呢？其实就是等于 A 乘上 S hat， 就是我的 P。而你也可以把这个视为 P 视为是什么？就是 B 这个向量投影到这个 column space 的这个投影的值，好，它的投影的向量就是 P。那我投影过去之后，这个就是我在这个平面上与 B 这个向量最相近的 那个向量的。好，那这中间呢有一个误差，好，那这个误差呢就会在 A 的 column space 它的 orthogonal complement 上面，所以这里呢其实是正交的。Okay, so this is the brief review of this square solution. But in previous slides, we didn't tell you how to calculate the least square solution, right? So now we go to find the vector x hat to satisfy the equation 1. Equation 1 is this. We want to find the vector x hat to satisfy this equation. Okay? So how can we find that? Because the residual is in the orthogonal complement of the column space. And from theory 5.2.1, if you already forget, please go back to check theory 5.2.1, where we said that the orthogonal complement of the column space is equal to the null space of A transpose. Okay, remember that? Okay, in that part, we described the relation between the column space of A, the row space of A, the null space of A transpose, the column space of A transpose. Right? Remember that? Okay. So, because the residual should be in the orthogonal complement of the column space of A, which also means the residual should be in the null space of A transpose. Right? So this should be satisfied. So if this satisfies, that means A transpose times residual should be equal to 0. Right? Because the residual is in the null space of A transpose. And we substitute the residual by B minus A s hat. Right? So A transpose times B minus A s hat should be equal to 0. So if we do some rewrite, then we can get A transpose A x hat is equal to A transpose B. Okay? So the vector s hat we want to find should satisfy this equation. A transpose A s hat is equal to A transpose B. Okay? So to solve the least square problem, we must solve this system. Okay? And here, the equation number 2. This equation represents an n by n system of equation, because remember, A transpose A should be n by n. A is an m by n matrix. A transpose should be n by m matrix, right? So if you multiply A transpose with A, it should be n by n matrix. So here is an n by n matrix times x should be equal to A transpose B. Okay. So how to solve this system? In general, it's possible to have more than one solution to the normal equation. Okay, we say this equation is called normal equation. So when you want to solve this square problem, you need to write down the corresponding normal equation. And there may be more than one solution to the normal equation. Okay? But in the following, we will show you actually we only have one unique least square solution. That's here. So if S hat and Y hat are both solutions to this normal equation, and since the projection of P of B onto RA is unique, then because the A S hat should be the projection of P of B onto RA, because the projection should be unique, so A S hat should be equal to A Y hat should be equal to P. Okay, so in fact this square solution is unique. Okay. How to solve it? Basically, when you try to find the x, you just pre-multiply the inverse of A transpose A, so that S hat is equal to the inverse of A transpose A times A transpose B. This is the unique least square solution to the linear system. Okay, so basically when you want to solve the least square solution, you just write down this formula, then you can find the least square solution. Okay, but things this formula seems incomplete, because how do you know we can derive this formula from this one to this one? You need to prove that the A transpose A is invertible, right? Only if this matrix is invertible, then you can do this kinds of calculation. So here we need to show that A transpose A is non-singular or is invertible. Okay, only if the A transpose A is invertible, then you can write down this formula. Okay, so if whether A transpose A is invertible or not. Okay, so let's prove it. Let Z be the solution to this system. So A transpose AX equals to 0. Okay, and if Z is a solution to this, then AZ should be equal to the null space of A transpose. Why? Because A transpose AZ is equal to 0, right? And if we consider these two together, these two first, then this is someone. The A transpose times someone equals to 0 vector. That means AZ is in the null space of A transpose. Right? Okay. So A times Z is in the null space of A transpose. But obviously AZ is also in the column space of A, right? Because Z, this matrix A times vector Z, the result would be in the column space of A. And then remember that the column space of A is equal to the orthogonal complement of the null space of A transpose, right? Okay, so in this case, think of AZ as a projection of Z by A. So now we know that AZ is in the null space of A transpose. It is also in the orthogonal complement of the null space of A transpose. Okay, so obviously AZ is in the intersection between these two subspace, and the intersection of this one and its corresponding orthogonal complement would be 0 vector. Therefore, we know that AZ is equal to 0. Okay? Okay. If AZ is equal to 0, now A has rank n. A has rank n. It's a n by n matrix. Okay? And the column vectors of A are linearly independent. Right? Because A is an no. A is a m by n matrix. If its rank is n, then the column vectors of A are linearly independent. So that Ax equals to 0 has only the trivial solution. Right? So if Ax equal to 0 has only the trivial solution, that means here the vector z should be equal to the trivial solution 0 vector. Oh, okay. So in this case, we know that the vector z is a 0 vector. That means A transpose A z equals to 0 has only trivial solution. Right? So by theory 1.5.2, if a system, if we take the A transpose A as a matrix, this matrix times X equals to 0 has only trivial solution. That means A transpose A is non-singular. So that we can write down this formula to calculate the unique least square solution. Okay? So this is a beautiful proof that connects many parts of the linear algebra. Okay? So let me repeat this in Chinese again. 好，这个部分的证明其实蛮漂亮的，它串接了好多我们之前讲的几个概念，所以如果你没有弄懂的话，你会跟不上这个证明。啊，所以你如果你看得懂每一步它是怎么推下去的，就代表你前面有融会贯通。好，我们现在呢就是说，当我们要解一个最小平方问题的时候，就告诉你说呢，其实啊，你就带这个公式就结束了啦。好，但这个公式成立的一个前提是说，你 A transpose A 必须是可逆矩阵。好，那怎么证明它可逆矩阵呢？那我们现在它的证明法其实有点 tricky。假设令 z 是 A transpose A 乘 x 等于0的一个解，也就是说呢 ，A transpose A 乘 z 等于0。好，那既然如此的话，我们如果先把 A 乘 z 括号起来，因为 A 乘 z 乘起来是一个向量嘛。好，其实 AZ 这个向量，左边乘上 A transpose 就会等于0嘛。那也就代表说 AZ 这个向量是在 A 的 transpose 的 null space 里面。而我们又知道，任何一个人就是 A 乘上某一个 Z， 这个结果一定是在 A 的 column space 里面啊，对不对？好，那 A 的 column space 就等于是 A 的 transpose 的 null space 的 orthogonal complement 啊。好，这边呢就是之前我们在讲几个不同的 subspace 之间的关系的时候，大家弄得头昏脑胀，好像在绕口令那一边。好，所以我们就知道它是这样了。好了，所以 AZ 这个向量又在 A transpose 的 null space 里面，又在同样这个 subspace 的 orthogonal complement 里面，那就代表说这唯一的交集就是0向量嘛。所以我们就知道说 AZ 等于0向量。好， 那今天 A 的 rank 等于 n，A 本来是一个 m by n 的矩阵，而 m 大于 n 嘛。那如果今天它的 rank 是 n，那就代表说 A 的 column vector 是线性独立啊。好，这个又是牵扯到我们之前的某一章讲线性独立的时候。如果 A 的 column vector 是线性独立，那么 AS 等于0就只会有 trivial solution 了。那也就是说，我们刚刚前面讲的 AZ 等于0只会有 trivial solution， 那也就代表说 Z 一定是零向量啦。Z 一定零向量啦。好，那 Z 是什么？不要忘了 ，Z 是我们说它是 A transpose A 乘 Z 等于0的一个解，那就代表说 A transpose 那乘上 Z 只有 trivial solution 啦。那不就代表又回到第一章了？有一个矩阵乘上 x 等于0，只有 trivial solution， 那就代表这个矩阵是 non-singular 啦。好，所以呢，我们就可以放心的写下这一个公式来求最小平方解。Okay? So, this square solution is, we can write down the formula. And the projection vector P is equal to A times S hat. And this is S hat. So we pre-multiply the matrix A. Okay? And the projection vector is the element in the column space of A that is closest to B in this square sense. Right? So here, if we consider this together, A times A transpose A inverse times A transpose, that is this part. This part. This constitute a matrix P, capital P. This matrix is called the projection matrix because what does this matrix do? This matrix make a vector B. We do the orthogonal projection to P. So P is equal to PB. This matrix, capital P, is called the projection matrix. It helps us to project the vector B onto the column space of A. Okay? So this is the projection matrix. It's just like a linear transformation. So remember the previous chapter, chapter 4, we talked about linear transformation. So the orthogonal projection is a kind of linear transformation. Okay? So let's check some example. Find the least square solution to this system. So now we have 3 equations, 2 unknown. So in fact, if you use the Gaussian-Jordan elimination, you cannot find any solution for this linear system. So you can only find the least square solution to this system. So how can we do that? We just write down the matrix A, 1, negative 2, 2, 1, 3, negative 1. And then A transpose. And then the vector B, 3, 1, 2. And then we solve this normal equation. A transpose, A times X equals to A transpose B. Right? So you can do some calculation, and finally you can get this. This is the corresponding this square solution. Okay? So finding this square solution is actually very important in engineering problems, because scientists often collect data and they try to find a functional relationship between the variables. For example, if we measure the temperature of a liquid at times T0, T1 to Tn, and then we measure the temperature as capital T0, capital T1 to capital Tn. Okay, so it seems that there is some relation between time and the temperature, because we may try to heat the liquid. Okay, so if we heat with more time, then the temperature goes high, and we want to find the relation between time and the temperature. So if the temperature T can be represented as a function of the time T, this function can be used to predict the temperature at future times. So why do we want to find the relation between them? Because we want to predict, okay? We can predict if we heat for more than 1 minute, how high will be the temperature be? Okay, so we want to do prediction, and this is highly related to um, the most popular technology you see today, machine learning. Okay, in machine learning technologies, we usually need to construct a model. We say model, actually we just try to describe the relationship between many variables so that we can predict the result based on some value of the variables. Okay, so in fact this is exactly what we talk about machine learning today. Okay, so now if the data consists of n plus 1 points in the plan, it's possible to find a polynomial of degree n or less passing through all the points. Okay, so theoretically, if you have n plus 1 data points, we can find a polynomial of degree n that pass through all the points. Such polynomial is called the interpolating polynomial. For example, if we have a plane here, if we have a data point this one and this one, it would be possible to find a polynomial passing a curve passing all these data points. For example, here, this curve, we can find this curve, and this is the so-called interpolating polynomial. Okay. However, because usually we have many data points, and it is less interesting to find a very high degree polynomial. For example, in this example, a straight line may be more appropriate to describe the trend or the distribution of the data points. Okay, so in this case, we would rather find a simpler polynomial to fit the distribution. Okay, and it's often impossible that the function passing through all the points, since the data usually involves experimental error. So if we just only allow you to use a straight line to describe the data points, then this straight line will not pass through all the data points. Okay, so indeed, lower degree polynomial that do not pass through the point exactly usually give a truer description of the relation between the variable. Okay, because you to get the data points, we would measure, for example, we would measure the temperature. However, we always have the measurement error. So if we insist to find a polynomial to 100% path through all the data points, then you will need a very high degree polynomial, which is not good in practical cases. Okay. So for example, if the relationship between the variable is actually linear and the data involves slight errors, it would be disaster to use an interpolating polynomial. We can see this example here. Now we have many data points, several data points, this one, this one, this one, this one, and so on. And at each time, there are slight measurement error. So in fact, this 1, 2, 3, 4, 5, 6, 7, 8, 9, these 9 data points are not exactly on a straight line. So if you insist to find a polynomial to 100% pass name, then you will get this polynomial. This one, which is very complex. Okay? However, this straight line may be more appropriate to describe the thread of the data points. So in machine learning, we call this polynomial is actually overfitting to the data points. Okay, if you have already had some concept of machine learning, you should heard about this term before, overfitting. That means you use a too complex model to describe the data. So this overfitting model may not be good when you use to predict, when you use to make prediction. Okay, for example, if the time number 9, actually a better predicted result would be this value. However, if you follow this interpolating polynomial, this polynomial may be looking like this one and so on. So the prediction would be this one. And the prediction error would be quite high. Okay? So let's see some example. If you are given a set of data at the position S1, S2 to Sn, the corresponding result is Y1, Y2 to Ym. Okay? And if we assume the relation between S and Y is a straight line, so this is a straight line equation, right? Y is equal to C0 plus C1x, where C1 is the slope, right? And the C0 is called the offset. 斜率跟截距 ，C1 是斜率 ，C0 是截距，对不对？好，我们用一条直线方程式来描述 S 跟 Y。So now the problem is, how can we find the coefficient C0 and C1 so that this straight line best fit the distribution of the data points? Okay? So because we have a set of data points, that means we would like to y1 equals to c0 plus c1 x1. y2 should be equal to c0 plus c1 x2. To ym should be equal to c0 plus c1 xm. In fact, this table tells us this relationship, right? And obviously, we have m equation. We have two unknown, C0 and C1, right? So this is a linear system. This is an overdetermined linear system, obviously, right? So we require the relation between S and Y should be here. So if we write down the corresponding linear system in a matrix form, then we can rewrite this linear system as 1s1, 1s2 to 1xm times c0, c1 equals to y1, y2 to ym. This is the matrix A. This is the vector C. This is the Y. Right? And we want to find the best C to satisfy this equation. And obviously, because this is an overdetermined system, so in fact, we are not able to find a solution. This linear system has no solution. Usually, it has no solution. So the only thing we can do is to find this square solution. How can we do that? So let's see some example. So if s is equal to 0, y is equal to 1, x equals to 3, y is equal to 4, and so on. So we just write down the corresponding linear system AC equals to y. So the matrix A is 1, 0. What is 0? 0 is the first x. 1, 3. 1, 6. Right? And what is 1? Why 1 first? Because remember that we assume y is equal to c0 plus c1x. So 1 means this. Okay. Okay. 1x. c0, c1. Okay. And y is equal to 1, 4, 5. Now, we just follow the formula of this square solution. So we just write down the corresponding normal equation and solve it. So finally, we can get C0 should be equal to 4 divided by 3. C1 should be equal to 2 divided by 3. So the corresponding straight line, the corresponding equation for the straight line is y equals to 4 divided by 3 plus 2 divided by 3 times x. So this is the equation of the straight line that best describes the distribution of this table of data. Okay? Okay. So this is, we should take a break.